Hello friends, let us continue discussing delta modulation. In the previous lecture, we saw that delta modulation is 1-bit quantization and it leads to a very simple implementation and much lower bit rate. But those advantages do not come for free. There is a cost involved, and the cost is in terms of quantization noise. In this lecture, we'll talk about the quantization noise in a delta modulator. There are two types of quantization noise in a delta modulator. One is the slope overload noise, also called slope overload distortion. And the second is called granular noise. We'll look at these two types of noise in delta modulation, and we'll also compute the quantization noise power in a delta modulator and compare it with that in PCM. So what is slope overload distortion? So consider a signal m of t which is to be delta modulated, and suppose we start here generating a DM wave. Say this is the sampling interval Ts, and say this is the step size delta. So because here the actual sample value is greater than the approximated quantized value, we have to take a positive step, we go up. Now at the next sampling instant, again the error is positive and therefore we go delta up. And this continues. And indeed what we find here is that instead of following the actual wave m of t, our staircase approximation is going away from this m of t, and it is not representing the original signal m of t. So it leads to a distortion known as slope overload distortion. Why is it occurring? The reason is that the slope of the message signal, say here at any point we consider, this slope of mt, that is dmt by dt, the magnitude of this slope is larger than the slope of the staircase function. And what is the slope of a staircase function? So this is the height delta step size, and this is the base ts. So delta by ts. So slope overload distortion occurs when dmt by dt, the slope of the message signal, is greater than delta by ts, the slope of the staircase function. But not only in this case are we observing a slope overload distortion. Suppose this is our message signal m of t, and we try to generate a DM wave here. Because now the error is negative, we go delta down. Error is still negative, we go delta down further, and so on. And we still observe the same phenomenon as we are moving away from the actual message signal, and therefore we again have a slope overload distortion here. And what is the reason? The reason is same. The reason is that here the slope of the message signal dmt by dt, that is larger than the slope of this, and because the slope is negative here, we look at the magnitude of the slope, and this slope is still larger than delta by ts, the slope of this staircase waveform. And therefore what we write here is that the slope overload distortion occurs whenever dmt by dt, its absolute value, and the maximum of this absolute value is greater than the slope of the staircase function. So what to do to avoid the slope overload distortion? The slope overload distortion will not occur if dmt by dt, the maximum value of its magnitude, is less than delta by ts, or we can say that the slope of the staircase function delta by ts is larger than the maximum absolute value of the slope of the message signal, and that is the condition to avoid slope overload distortion, a very important result. The second kind of distortion in delta modulation is what is known as granular noise. Consider a message signal of this sort. Suppose this is the message signal m of t, and we try to generate a delta modulated wave for it. And suppose we are here and we start, and this is our step size, this is ts. Because error was positive, we went delta up. Here the error is negative, we need to come delta down. And again the error is positive, we go delta up. Again the error is negative, we go delta down, and so on. So what we observe here is that all the signal variations are within the step size delta. What happens is that we get alternate positive and negative pulses, and therefore when it is passed through a low pass filter for reconstruction at the receiver, we get a straight line, all variations are lost, and therefore the information is lost. So the reason for granular noise problem is that the step size is much larger, such that all the signal variations are within the step size, and therefore we get alternately positive and negative pulses. How do we quantify this quantization noise power? So we note that when our signal is properly followed by a DM wave, say we have a proper step size so that we are able to follow the signal properly, what is the maximum error that can occur? Clearly the maximum error, the quantization error, is a random variable if we represent it by q. That maximum error can be delta or minus delta. So we say that the quantization noise is a random variable that is uniformly distributed in the interval minus delta to plus delta. So if we draw its PDF, it is rectangular, of course, and uniform in the interval minus delta to plus delta, and therefore this PDF is 1 by 2 delta because the area must be unity. So this is FQQ. If we compute the mean value of it, is clearly by definition integration minus infinity to infinity q FQQ dq, and because FQQ is non-zero only in the interval minus delta to delta, so minus delta to plus delta q into 1 by 2 delta dq, which clearly works out to 0. Now if you look at the mean square value, which is indeed the quantization noise power, it is by definition minus infinity to plus infinity q square FQQ dq, which is equal to integration minus delta to plus delta q square into 1 by 2 delta dq, or 1 by 2 delta we can write outside. Q square dq integrates to q cube by 3, limits minus delta to plus delta, and this works out to delta square by 3. So this is the quantization noise power for delta modulation. We can also work out the variance sigma q square, which is EQ square minus EQ whole squared, because EQ is 0. So sigma q square, the variance is same as the mean square value, delta square by 3. So this is a very important result, and we should memorize it, that the quantization noise power, whether we call it mean square value or variance, the same thing, because the mean value here is 0. We represent it by NQ. So what we observe is that the quantization noise power NQ for delta modulation is equal to delta square by 3, where delta is the step size. Recall that the quantization noise power for PCM was delta square by 12. Clearly, the quantization noise power for PCM is 4 times smaller than the quantization noise power for DM. So this is the price actually that we pay for simplicity of delta modulator. So the quantization noise power of delta modulator is higher than that of PCM, and therefore the signal to quantization noise ratio SQNR for a delta modulator is poorer than that of PCM. Now if we again examine the slope overload distortion and the granular noise together pictorially here, we notice something very interesting. The slope overload distortion occurs because the slope of the staircase approximation is smaller than the slope of the message signal. The remedy would be to increase the slope, and the slope can be increased by increasing the step size, because we cannot reduce TS because that has been fixed by design, the sampling interval. So for a fixed TS, the slope of the staircase function, the DM wave, can be increased by increasing the step size. But if we increase the step size, what we observe that granular noise is occurring because the signal variations are small and therefore they are contained within the step size. The solution for granular noise problem would be a smaller step size. So if we want to solve the slope overload problem, we have to increase the step size. If we want to solve the granular noise problem, we have to decrease the step size. So there is a dilemma. If we try to solve one problem, the other one occurs. So what we note that in delta modulation, a small step size leads to slope overload distortion. The solution is use a large step size. If we use a large step size, it leads to granular noise problem, and the solution is to use small step size. So what is the ultimate solution? How can we handle both? The solution is to have an adaptive mechanism which can increase the step size when the slope of the message is large, and which can reduce the step size when the signal variations are small. And this is achieved in an adaptive delta modulator. This is what we'll see in the next lecture. Thank you.